Hello, today's section is section 3.5, implicit differentiation and the derivative of ln of x. Before we get into the process of implicit differentiation, I want to draw a distinction between two different ways of defining a function. So far, whenever we define a function, if we were doing it algebraically with a formula, we would come up with some explicit equation for the function. And so we might call these explicitly defined functions. And they look like y equals f of x, right? So whenever we had a formula, y equals x squared, y equals square root of x plus 5x, etc. These are all explicitly defined. And so again, we're defining the variable y explicitly in terms of x. So if I were to pick some x value, like x equals 4, we could plug it in and we would get some output, 16. Right, using y equals x squared. It turns out that we can define functions implicitly as well. And the idea with an implicitly defined function is that we have some equation with both x's and y's, but it's not in the form of y equals f of x. In other words, it isn't solved explicitly for y in terms of just x. So for example, x squared plus y squared equals 9. And obviously, this isn't y equals a function of just x. And even if I were to try to solve it for y, I would get y squared equals 9 minus x squared. So it's not quite in the form of y equals a function of just x. If I take the square root, I would get y equals plus or minus the square root of 9 minus x squared. Because remember that the square root of something squared is plus or minus that quantity. And so here actually this one implicitly defined expression, x squared plus y squared equals 9, turns out to correspond to two explicit functions, y equals f of x. One for the plus, one for the minus. The situation can get a lot more complicated if you have, right, the x squared plus y squared equals 9 isn't all that difficult to deal with. It's not that difficult to solve for y. But we can come up with examples where it's actually maybe impossible to solve for y in terms of just x. Right? I think if we were to try to solve this equation, y to the 7 plus xy equals x squared plus y, for just y in terms of x, we'd run into a bit of trouble. Now, it might be the case that even when we can only define a function implicitly in terms of another one, in terms of another variable, we still might want to be able to compute its derivative. Right, so here, for example, if y is equal to 1, maybe I could solve it for x, right? And so that would be 1 to the 7 plus x equals x squared plus 1. I can subtract 1 from both sides, and so that would give me x equals x squared. If I subtract x from both sides, I get 0 equals x squared minus x, which has two x solutions, x equals 0 and x equals 1. Right, so for my one input, y equals 1, I get two outputs, x equals 0 and x equals 1. Likewise, we could, if we really want x to be the input, if x is 0, right, I would then try to solve for y. So I would have y to the 7 equals y, and then I could solve for y, right? Maybe y would be 1 or 0. Okay, I get some outputs for y, with an input for x. And so even though this expression is not given explicitly, I'm still able to think about y as a function of x, right? Even though I don't have the formula for it. And so sometimes we will want to compute dy dx when y is defined implicitly with respect to x. And in this case, what we want to use is the process of implicit differentiation. I'm going to write down the steps, and then we'll look at an example. And if you have questions after trying the problems in the book, we can talk about it in class. So here are the steps for implicit differentiation. In particular, to find dy dx. So assuming the variables are x and y, and that y is a function of x. First, we're going to differentiate both sides of the equation with respect to x, because that's what we're treating as the independent variable. In step 2, as we compute the derivative of both sides, we're going to come across occurrences of both x and y. The occurrences of x that we come across, we will just differentiate in the usual way. But when we come to an occurrence of y, we have to remember that y is a function of x. And so when we differentiate a y term, say, we must remember to multiply by dy dx after doing the derivative, as we normally would. Okay, and the reason for this is the chain rule. Okay, the chain rule is what forces us to need to multiply by the derivative of y with respect to x in this step. As you'll see in the example in a moment, after step 2, where we've differentiated both sides, doing the x terms in the usual way, doing the y terms in the usual way, but then remembering to multiply by dy dx whenever we differentiate a y term, what we'll end up with is some equation that has x's and y's, and also dy dx's. And then in step 3, what we'll have to do, because it's what we're looking for, is we'll have to solve for dy dx. So in this step, we need to do some algebra. All right, let's look at an example. This is a special case of 3.5 number 6. We're given x squared minus 2xy plus y cubed equals 8. Okay, as we can see, this equation is not in the form of y equals a function of just x, and so this defines y as a function of x, but implicitly. All right, and so what we're thinking in our heads here is that y is equal to f of x, even though I don't see f of x in the formula. Okay, we're still treating y as depending on x. And now what I want to try to do with this in this problem is to compute dy dx, the derivative of y with respect to x. All right, we've seen many examples in this class already of why derivatives are useful and something that we might want to compute, and that's also the case here. So we're going to use implicit differentiation. All right, and so I just go through the algorithm. Right, with step 1, I'm going to do the derivative with respect to x of both sides of the equation. Right, there's the derivative with respect to x of the left-hand side, and that needs to equal the derivative with respect to x of the right-hand side. We're going to do this, the next step here, in a few steps. On the right-hand side, the derivative of a constant with respect to x is still 0, like it normally is. When I differentiate x squared with respect to x, I just do that in the usual way. So that's 2x. And then I'm going to have a subtraction, right? I know when I do the derivative and I'm subtracting, I can subtract the two derivatives. So I'm going to have a minus the derivative with respect to x of 2xy. And then I'm going to have the plus the derivative with respect to x of y cubed. All right, before I deal with this middle term, the derivative of 2xy, let's look at the derivative with respect to x of y cubed. Like I said in step 2 of the process, whenever you differentiate a y term, you do it like you normally would. In other words, I'm going to get 3y squared. But then because it's a y term, I have to remember to multiply by dy dx. So this is 2x minus the derivative with respect to x of 2xy, and then plus 3y squared, and then times dy dx. All of that equals 0. I still have one other term to deal with, right, this term in the middle. For this term, I have 2x times y, so I'm multiplying. Whenever I want to do the derivative of a product, like we've seen, we have to do the product rule. So we're going to do the product rule for that term. Okay, coming up to the top here, here's 2x and then a minus, and then I'm going to have, from the product rule, the following. The derivative of 2x is 2 times the second function, which is y, and then plus the first function, 2x, times the derivative of y with respect to x. The derivative of y, if we kind of did it normally, would be 1, but because it's a y term that we're differentiating, we have to multiply by dy dx. So we get just dy dx there. What's left in the equation, I still have the plus 3y squared dy dx, and then equals 0. Okay, at this point, I'm done with step 2 of the process. There were 2 separate times where I had to differentiate a y term, and when I did that, I ended up multiplying by dy dx. So like I said, for step 3, after the differentiation, I have some x's in my formula, I have some y's in my formula, and I also have dy dx in the formula, which is good, because that's what I'm trying to find, right? That's what I'm trying to compute in this example. Right, so with step 3, I have to solve for dy dx. All right, we'll do a little bit of simplifying here. First, in particular, I'm going to distribute the negative. So this is 2x minus 2y minus 2x dy dx plus 3y squared dy dx. Right, I have to keep track of these dy dx's because I'm going to solve for those. This all equals 0. Like we're used to from algebra a long time ago, in order to solve for a particular quantity, we should get that quantity on one side of the equation by itself, right? So everything else can move to the other side. In particular, let's subtract 2x from both sides. Let's add 2y to both sides. That would give us negative 2x dy dx plus 3y squared dy dx equals what? We subtracted 2x. We added 2y. Now, on the left-hand side, I still see what I'm trying to solve for. And in particular, I see that dy dx is in common to both of these terms. So, here we factor. Okay, this is typical of this kind of problem. You're typically going to factor at the end in order to get dy dx by itself. When you factor it out, what's left? Well, the coefficients, negative 2x plus 3y squared. And here's dy dx, we factored it out. This equals negative 2x plus 2y. As a last step, to get dy dx by itself, I have to divide both sides by the term in parentheses. So, dy dx, in this case, equals negative 2x plus 2y divided by negative 2x plus 3y squared. one thing that you'll notice with implicit differentiation is that at the end, when you get the derivative dy dx, it will typically depend on both x and y. That's different than when you have an explicitly defined function. However, anything that we did before with dy dx with the derivative, we can still do with the derivative here. Let's continue this example. And we'll go ahead and find a tangent line to the curve defined implicitly. All right, so this is a continuation of the example. Let's find a tangent line to this curve, x squared minus 2xy plus y cubed equals 8 at the point 0, 2. Like we're used to for a tangent line, we need a point, which we have, in this case 0, 2, and we need the slope, m tan. M tan, just like it's been all semester, is the value of the derivative dy dx at the particular point that we're looking at. And so in this case, I want dy dx evaluated at xy equals 0, 2, at the point 0, 2. A second ago, we just computed dy dx, the derivative. And now, to get the slope, I plug the point, 0, 2, into the formula that I came up with for dy dx. So that looks like this. The formula for dy dx was negative 2x plus 2y divided by negative 2x plus 3y squared. I want to evaluate this at xy equals 0, 2. What's a little bit different this time than what we're used to is instead of just plugging in x equals 0, for example, we have to plug in both x and y. But that's easy enough to do. So m tan is negative 2 times 0 plus 2 times 2, all over negative 2 times 0 plus 3 times 2 squared. And this turns out to be 4 over 12, or 1/3. And so that's the slope. We know the point is 0, 2, we know the slope is 1/3, and so using our point slope formula, the tangent line is y minus 2 equals the slope, which we just found is 1/3, times x minus 0. We've differentiated many functions in this class. All right, we learned the power rule a long time ago. We learned the addition and subtraction rules. We saw that the derivative of e to the x is e to the x. We've learned now the product rule and the quotient rule and the chain rule. That was a good one. What we don't yet know how to do is we don't yet know how to differentiate ln of x. So let's see if we can find the derivative of y equals ln of x. So, if y equals ln of x, what I want to try to find is dy dx, right? That's what I'm looking for, the derivative of ln of x. Here's how we'll do it. Y equals ln of x. If I rewrite this with exponentials, or if I do e to both sides, y equals ln of x is the same as if I had e to the y equals e to the ln of x. In other words, e to the y is equal to x, because e and ln cancel. This equation now, e to the y equals x, this defines y implicitly in terms of x. Look at that. So, if this is an implicit equation for y in terms of x, and I want to find dy dx, what I have to do is use implicit differentiation. All right, well, I know the steps. Let's differentiate both sides of the equation with respect to x. On the right-hand side, the derivative of x with respect to x is 1. That's just the normal thing. On the left-hand side, when I differentiate a y term, like e to the y, I have to remember to multiply by the derivative dy dx. So that's e to the y times dy dx. What I'm trying to solve for is dy dx, and so in this case, to do it, there's not a lot of algebra involved. I just need to divide both sides by e to the y. In other words, dy dx equals 1 over e to the y. Now, since y is a function of x, explicit function of x, I kind of want dy dx, or I definitely want dy dx, to be a function of x as well. But it is, because what does e to the y equal? E to the y equals x. And so here, if I just replace e to the y with x, I get my formula, 1 over x. All right, to write it down, here's what we should remember. d dx of ln of x is equal to 1 over x. This is useful to remember. You should memorize it. Let's do a couple of examples here. This problem will be to find f prime of x. F of x, the function in this case, is 3 ln of x plus x to the 5th. So what's f prime of x here? Well, I try to differentiate 3 ln of x plus x to the 5th. Because I'm adding, I know that I can do the derivative separately. The derivative of x to the 5th is 5x to the 4th, of course. The 3 here is a constant multiple, so it's going to stay. And then from just a minute ago, the derivative of ln is 1 over x. So here's our answer. Two more examples, slightly more difficult. Let's say f of x is x cubed ln of x plus 2. And I want to find f prime. For f prime, I do the derivative of x cubed times ln of x plus 2. The plus 2 is going to go away because the derivative of a constant is 0. And so now I have to differentiate x cubed times ln of x. Ultimately, this is a product. And so to do the derivative, I need the product rule, right? I still have to do my old rules whenever they come up. The derivative of the first term is 3x squared times the second term, which is ln of x, and then plus the second term, x cubed, times the derivative of ln, which is 1 over x. Let's do one last example with differentiating a function involving the natural logarithm. Let's find g prime of x if g of x is equal to ln of x to the 7 plus x. So now this is slightly more difficult because, well, let's call this h, I guess, h prime of x. The reason why this is slightly more difficult is that because now I see that my function that I'm trying to differentiate is a composition. Okay, the inside function is what's inside the logarithm. For the chain rule, we've been calling that g of x, so x to the 7 plus x. And the outside function, f of x, in other words, is ln of x, the natural log. I have to do the chain rule to differentiate a composition. I remember from the chain rule that I need both the derivative of the inside, which is g prime of x, that equals 7x to the 6 plus 1. I need the derivative of the outside, the derivative of ln of x is 1 over x, so f prime of x is 1 over x. And now I need to put them together using the chain rule. h prime of x from the chain rule is f prime of the inside times the derivative of the inside. So, let's see, f prime, that was 1 over x. I don't want f prime of x, I want f prime of g. So instead of doing 1 over x, I have to do 1 over the original inside function. In other words, that's 1 over x to the 7 plus x. And then I multiply by the derivative of the original inside. I multiply by g prime, so I multiply by the quantity 7x to the 6 plus 1. You can write this as a single fraction, 7x to the 6 plus 1 over x to the 7 plus x. Let's do one more. 3.5, number 20. Here it is. A company conducted a survey regarding its new electric car and estimates that the selling price P of the vehicle in thousands of dollars and the number X of cars that will sell, measured in thousands, are related by this equation. Px squared plus 12px equals 28,000. As you can see, this equation does not define x or p explicitly in terms of the other variable, but it is an implicit expression for both p and x. I'm going to do half of this one, and then tomorrow if you have more questions, we'll do the other half. But let's compute and interpret dx dp when the selling price is 36,000. So the price, remember, is P. P is given in units of thousands of dollars. So if the selling price is 36,000, the P is 36. All right, so we're going to find dx dp at the moment when P is equal to 36. Because my equation is given implicitly, I use implicit differentiation to try to find that derivative. In this case, what am I differentiating with respect to? I'm differentiating with respect to P, and I'm treating x as a function of P. So whenever I differentiate an x term, I have to remember to multiply by dx dp. Okay, so we do the derivative with respect to P of both sides to start with. When I come to the P terms, I just differentiate them like I normally would. When I differentiate an x term, I do it like I normally would, but then I have to multiply by dx dp. So, in both of these terms here, p times x squared and 12p times x, I have to do the product rule for both of those. All right, here's what it looks like. The derivative of the first term, p with respect to p, is 1, times the second term, x squared, plus the first term, p, times the derivative of x squared with respect to p. So here I'm differentiating an x term, so that gives me 2x, like it normally would, but now times dx dp. All right, so these two terms came from this single product, from the product rule. Now we move on to the 12px, and again do the product rule. The derivative of 12p with respect to p is 12, times the second function x, plus 12p, first function, times the derivative of the second function. The derivative of x with respect to p is dx dp. On the right-hand side, the derivative of 28,000 with respect to p is 0 because 28,000 is constant. So, from the derivative now, I see two occurrences of dx dp, what I'm trying to solve for. So let's isolate that. We subtract 12x from both sides, subtract x squared from both sides. That gives us 2px dx dp plus 12p dx dp equals minus x squared minus 12x. Each term on the left-hand side now has a dx dp in common, so we factor it out. That leaves us with 2px plus 12p times dx dp. That's the factoring step, don't forget it. To finish, divide both sides by the term in parentheses. In other words, dx dp is equal to minus x squared minus 12x all over 2px plus 12p. So, we were supposed to find dx dp when the selling price is 36,000. In other words, when p is 36. So in my answer here, I can substitute in p is 36, but I also have to substitute in x. And so the question that remains is, what is x when p is equal to 36? To figure that out, you have to go back to the original formula, because the original formula relates p and x. So this is just some algebra. Okay, when p is equal to 36, what do we end up with? 36 x squared plus 12 times 36 times x equals 28,000. And if you solve this for x, I'm going to leave the algebra to you, I believe. You get x equals plus or minus, but we're going to take the positive root because x is a real quantity. So we get square root of 6892 over 9, if I did that correctly, which is about 27.6727 x's. What is x? I forget. X is the number of cars measured in thousands. So this is like 22,672 cars, approximately. And so now we can finish this. dx dp, the derivative that we computed implicitly, is minus x squared, so that's going to be minus square root of 6892 over 9 squared, minus 12 times x, so 12 times square root of 6892 over 9, all divided by 2 times p, which is 36, times the x that we found, square root of 6892 over 9, and then plus 12 times p, so 12 times 36. All right, we can figure out what this number is. I'll let you compute it on your calculators. I'll write a note about it. And then for the interpretation, what will that be? That's the rate at which x is changing with respect to p at the moment when the selling price, when the p is 36,000. So, what's x? X is the number of vehicles. And so this is the rate at which the number of vehicles changes with respect to price when the selling price is 36,000.